Hello, and welcome back to the course on distributed systems and security. In this video, which will actually be a series of 3 shorter videos, I will talk about consistent communication. The first video here, I will just use that to set the stage, consider what is the problem and how do we model the setting, and then give like the very first brief ideas of it. So what's the setting? Well, we'll be looking at flooding networks, where you send a message to everyone in a bigger network just by sending it to your neighbors that send it on to their neighbors and to their neighbors and so on. Or some other setting which have the property that when different parties send messages, they might arrive at different sites in different orders. And in fact, even messages sent by a single sender might overtake each other on the network and arrive in different orders at different sites. So that's how, if we don't want to make too brave assumptions on the internet, that's how the world will look like if we try to send, if a lot of parties try to send a lot of messages at the same time. Okay, so we start with some setting that's where the message delivery is unordered. And then we would try to create some order. And we will look at 3 different orders, one called FIFO, one called causal, and one called total order. So in the FIFO order, we would like to look at techniques for how we would enforce that messages sent by a single sender, at least, are delivered in the order that they were sent. By that I mean, at all places where both messages sent by me are delivered, they are also delivered in the order in which I sent those 2 messages. That's not too hard. Then we'll dive into something called causal order, where we want to enforce that also messages sent by different senders maintain some order in which they are delivered. More specifically, if 2 messages could have affected each other, then they will be delivered in the order in which this effect could have taken place. So if I send out a message which is a question, and someone else sends out a message that's an answer, I want that the question arrives before the answer at all sites where both of them are delivered, or at all sites. Okay? That's reasonable, because getting the answer before having the question could be confusing. And then in the very end, we will look at something called total order, where we require that all messages are delivered in the exact same order at all receivers. This is actually an add-on. I mean, that doesn't mean that the order makes sense. It could be that the answer is delivered before the question at all sites. The only thing we require is really everyone sees all messages in the same order. And then, of course, on top of that, we could require causal ordering. Causal ordering, on the other hand, is easy to see. That is a refinement of FIFO. So causal is something that takes something that is FIFO and then makes it even better. Because in FIFO, we say that 2 messages sent by the same party should arrive in the order they were sent. And of course, 2 messages sent from the same party could have affected each other. So if we do in causal order, we cannot swap these 2 when they deliver, because we might be swapping 2 parts of the text that's supposed to be read in this order here. Yeah. Good. So let's dive into it. So first, the attack model of this video and the next 2 is pretty optimistic. So we're going to assume that all processes are correct. So there are no crashing processes now, and there's no processes that is trying to screw up our protocols. We will also assume that somehow we have managed to authenticate all channels such that the adversary cannot inject messages, cannot claim to send something on my behalf. But the adversary is allowed to arbitrarily delay and reorder messages. So it can take a message I send and deliver it in 2 days, and then take the next message I send and deliver it in a second. That is allowed. And then we will do without using physical clocks. So it's a protocol for the asynchronous model, fully asynchronous model where we don't use time at all. So that's the setting. It's a very optimistic setting, but it will allow us to think about ordering and in particular about causality in distributed systems. And it's good to learn that in a simple setting. Then we can apply it to more complicated settings later. So we're looking at flooding networks, as I said. So we imagine that messages travel in the following way. If P1 here wants to send a message to everybody, it will just send it to its two neighbors. And then they will pass it on to their two neighbors. P3 will pass it on to its two neighbors. You'll see that everyone has two neighbors in here, or two parties they're sending to, and the message spreads like that, which easily can give rise to a quite unorderly delivery, in particular if two parties are sending at the same time. And then we'll use the following figures for how messages are sent and delivered in this network. So one party, let's say party 1, will be a line, so time travels from left to right. Party 2 is another line. Party 3 is a third line down here. And then we use an incoming error like this to mean that a message was sent. Okay, so that means P1 received on its API from its user the message M1 and was told, please send M1 to everybody. And if you read the book, you'll see that the way we model the network is using a network resource in our fine system model. That is just a box that will take messages as input, and then if they're told to deliver the message by the adversary, they will deliver it at the other side. Right? So it means that when a message here is sent, it's formally just stored inside this ideal functionality called flood. And then at some point, the adversary can come and say, it's now time to deliver M1 to party 2. And we draw that as follows. So we draw an outgoing error. That means M1 got delivered there. And then to make the figures easier to look at, more intuitive to look at, we draw an error like this showing that M1 was sent down here, boom, and delivered. Okay. But formally it's just put into a box and it sits there, and the adversary out tells when we want to output it at party 2. That's all there is to it. You will see when you see the formalization of this box that it can happen that we have what is called delayed local delivery. That means a message is sent at party 1 and then only later delivered at party 1. That might sound a little bit silly. Why don't I just deliver the message when I know I want to send it? But in fact, later when we look at total order, we can't do that. Because if two messages are sent at the same time at two different parties and both of them deliver it immediately, then when they get each other's messages, they would be cooked, because no matter how they now deliver these, they will each have delivered their own message first. And if we want to deliver all messages in the same order at all sites, one of them will have to postpone delivering its own message until it receives the other message. That's a dragon we will be fighting later. Well, that's why we have this notion of delayed delivery. And we just draw that as follows. And it also means in the algorithms, when I say that a party sends M1 to all other parties, it includes itself. Okay, and so it sends it to all parties, not all other parties. Okay, so that's how we read these figures. And then, as I said, we will be looking at 3 different orders we would like to implement. One is called FIFO, which says that messages from the same party arrive in the order in which they were sent at all the other parties. Causal say that if message A could have influenced a message B, then A arrives before B at all other parties. And finally, total, as I said, all messages arrive in the same order at all parties. Let's try to implement FIFO. So here, the only thing we want to mitigate is the fact that if I send 2 different messages, one of them could overtake the other one. That's pretty easy to handle, right? We just put sequence numbers on messages. So whenever I send a message, I number it, number 1, 2, 3, 4, and so on. And then in the other end, everyone else will just make sure to deliver my messages in the order in which they were numbered. So if so far they delivered my second message and they get message number 4, they just postpone it, they put it in a box. Then when they get message 3, they deliver message 3, and then they look in the box and see, hey, I have message 4, and then they deliver message 4. In real life, there's a lot of stuff to combat there with trying to get finite size buffers and so on. But that's basically the idea. So it would look something like this here. We have a network of messages traveling. Party 1 sends M1, it arrives here, gets output. M1 takes a long time here to travel down here and get delivered at party 3. So in the meantime, party 1 sends a second message. We're putting the counters up here in the exponent that actually arrives first. But because it has a 2 on it, party 3 will know to postpone the delivery of this thing and then output M1 here when it comes. And to not confuse postponed delivery with postponed local delivery, we do a slightly different dashed arrow like this. So that's how to read the figure. So that was very simple. That's not the most surprising algorithm in the world. And indeed, this was also just to set the stage and get used to these figures here.